low cloud bank, which sometimes hides the valley, is absent. Ooh, thank you so much for liking the live. Can we get 20 likes? 20. If you're lucky and the low cloud bank, which sometimes hides the valley, is absent, then just before landing there, you may glimpse a cluster of buildings less than a mile northwest of the airport. Like the tip of an iceberg. Your guys' favorite word, iceberg. The central administration buildings of the European Laboratory for Particle Physics, or Cern, the French acronym for the original, now politically incorrect name, European Council for Nuclear Research, belie a far more impressive structure hidden below the surface. The picturesque farmland and small hamlets dotting the French-Swiss border do not betray any evidence of one of the largest tunnels in the world. Traveling 26 kilometers in a vast circle ranging from about 50 to over 100 meters below ground is the Cern Large Electron Positron LEP Collider Ring, soon to house a new machine, the Large Hadron Collider, LHC. This book is a little old, so the collider is a thing already. To visit the Cern laboratory or any major particle accelerator facility today is to feel like Gulliver entering Brobdingnag, the land of the giants. Every object seems out of scale with mere human dimensions. The LEP tunnel itself, so that is the Large Electron Positron Collider Ring, for example, it's 26 kilometers long. It's wide enough inside to easily accommodate a modern sport utility vehicle or two, should it ever be turned into an underground racetrack. The tunnel is accessible from the surface at one of 4 different laboratory locations. At each site, one of 4 mammoth particle detectors can be found. Each is the size of an apartment building built deep below ground, contained in experimental halls that could dwarf the stage at Radio City. Each behemoth is constructed from thousands of separate components fabricated by hundreds of physicists and technicians hailing from dozens of countries scattered across the globe, and each is built to a precision of fractions of a millimeter. The MIT physicist Vicky Weisskampf dubbed such devices the Gothic cathedrals of the 20th century. From the start of construction to the completion of the first experiment, a decade can easily pass. This is in sharp contrast to the timescale of the processes being investigated, which occur in less than a billionth of a second. Such experiments repeatedly recreate and measure for a fraction of a second the conditions and interactions of matter and energy, including, as we shall see, the extremely rare events which may have been last experienced in our universe 10 billion years ago. The LEP collider imparted energies to elementary particles that were far beyond those produced anywhere else in our galaxy, except perhaps in the shock wave from an exploding star, or in the final collapse of a gigantic black hole. Charged particles were accelerated by electric and magnetic fields around the tunnel so that they traversed the Swiss-French border without passports near the airport and then again at the base of the Jura Mountains 10,000 times each second. In the process, they achieved energies of almost 1 million times the energy they store at rest. Yet these gargantuan values are still 1 million times smaller than the average energy carried by every particle when the universe was the size of a baseball. The collisions between individual particles at that time were so energetic that to recreate them with present technology One would have to build particle accelerators with a circumference bigger than the circumference of the moon's